Wid. You've probably heard this one before. Wid. Old churches. Wid. Old houses. Wid. Windows that are centuries old. Wid. Look closely at the glass, really closely, and you'll notice something strange. Wid. It's thicker at the bottom than at the top. Wid. For decades, there's been an explanation for this that gets repeated everywhere. Wid. In classrooms. Wid. In documentaries. Wid. In casual conversation. Wid. Tour guides say it in cathedrals. Wid. Teachers say it in science class. Wid. It gets passed along so often by people who sound so confident that almost nobody thinks to question it. Wid. The explanation is this: glass is actually a liquid. Wid. It just flows so slowly you can't see it happening. Wid. Over hundreds of years, gravity pulls it downward, and it pools at the bottom of the pane. Wid. It's a great story. Wid. It's clean, it's a little spooky, and it makes you feel like you're in on a secret most people don't know. Wid. There's just one problem. Wid. It's not true. Wid. Not even close. Wid. The real explanation is stranger, and honestly more interesting than the myth ever was. Wid. Physicists have actually written entire papers dedicated to debunking this one idea. Wid. Multiple times, over multiple decades, because it keeps coming back. Wid. Someone hears it in a museum tour, repeats it to a friend, and the cycle starts over. Wid. Rarely does anyone trace it back to where it came from, or ask why it spread so easily in the first place. Wid. Once you know the real mechanism, you'll understand exactly why the myth was so easy to believe, and exactly why it's wrong. Wid. To understand why glass is not a liquid, you first need to understand what a liquid really is. Wid. Because most people think the difference between a solid and a liquid is simple. Wid. It's not. Wid. We're taught in school that matter comes in three states. Wid. Solid, liquid, gas. Wid. Solids hold their shape. Wid. Liquids flow and take the shape of their container. Wid. Gases expand to fill whatever space they're in. Wid. The thing that supposedly separates a solid from a liquid at the molecular level is structure. Wid. In a solid, atoms lock into a fixed repeating pattern. Wid. A crystal lattice. Wid. Think of table salt or ice or a diamond. Wid. Zoom in far enough, and you'll see the same orderly arrangement repeating over and over, like a brick wall extending in every direction. Wid. In a liquid, that order breaks down. Wid. The molecules are still close together, still bound to each other, but they're free to slide past one another. Wid. No fixed grid. Wid. No repeating pattern. Wid. Just a chaotic, shifting crowd. Wid. So which one is glass? Wid. Here's where it gets uncomfortable. Wid. If you look at glass under a microscope, at the atomic level, its structure looks disordered. Wid. Chaotic. Wid. There's no repeating crystal lattice. Wid. In that specific sense, it actually resembles a liquid far more than it resembles a solid. Wid. Turns out the myth took hold for a specific reason. Wid. Scientists noticed decades ago that glass has this liquid-like molecular disorder, and somewhere along the way, that got translated into glass is a liquid in the popular imagination. Wid. Once that idea existed, the old windows became the perfect piece of supporting evidence. Wid. A visual you could point to. Wid. Proof you could see with your own eyes. Wid. Except that's not what's happening in those windows at all. Wid. Let's solve this properly. Wid. What is really going on with those centuries-old panes of glass? Wid. How glass used to be made is where the real answer lives. Wid. Before modern float glass manufacturing existed, glass panes were produced using a method called crown glass or cylinder glass. Wid. A blob of molten glass would be spun rapidly, using centrifugal force to flatten it into a disc. Wid. That disc was then cut into smaller panes to fit windows. Wid. Here's the catch. Wid. That process does not produce a perfectly uniform thickness. Wid. The spinning creates a disc that is naturally thicker toward the center and thinner toward the edges. Wid. When glaziers cut that disc into workable panes, many of the resulting pieces were already slightly thicker on one side than the other. Wid. When installers set those panes into a window frame, they made a very practical, very human decision. Wid. They installed the glass with the heavier, thicker edge facing down. Wid. Not because of physics forcing the glass to flow. Wid. Because it made the pane more stable in the frame. Wid. Gravity wasn't reshaping the glass over centuries. Wid. Gravity was just a factor in a construction decision made on day one. Wid. Old panes installed with the thick edge facing sideways or even facing up confirm it. Wid. If the flowing liquid theory were true, gravity would eventually pull the mass downward regardless of how the pane was originally installed. Wid. That's not what we observe. Wid. The thickness distribution stays exactly where the glaziers originally put it. Sideways glass stays thicker on the side. Upside down glass stays thicker on top. Wid. The glass never rearranges itself to obey gravity, which is exactly what you'd expect if it isn't flowing at all. Put simply, the visual evidence for the myth was never evidence for the myth. It was evidence of an old manufacturing process, mistaken for centuries of secret liquid movement. Modern glass doesn't have this problem at all, which is itself a clue. In the 1950s, a British engineer named Alistair Pilkington developed what's called the float glass process, floating molten glass on top of a bed of liquid tin so it spreads out into a perfectly flat, uniform sheet as it cools. Nearly every window made since has come from some version of that process. Uniform thickness, top to bottom, edge to edge. No thick side, no thin side, nothing for a myth to point to. If gravity really were dragging glass downward over time, modern windows made decades ago should already be showing some hint of that same lopsided thickness. They aren't. The old evidence stopped appearing the moment the old manufacturing method did, which is exactly what you'd expect from a manufacturing artifact, and exactly what you would not expect from a genuine liquid slowly obeying gravity. But the myth persists for a reason, and it's not just the windows. It's that offhand comment about molecular structure. The fact that glass really does have that disordered, non-crystalline arrangement usually associated with liquids. So if it's not a liquid, and it's clearly not a normal crystalline solid either, what is it? Scientists have a specific term for this. Glass is what's called an amorphous solid. Nobody just guessed this. Researchers confirmed it using a technique called X-ray diffraction, firing X-rays through a material and studying the pattern that scatters out the other side. Fire X-rays through a crystal, like quartz or table salt, and you get a sharp, orderly pattern of dots, a direct signature of that repeating atomic lattice underneath. Fire the same X-rays through glass, and the pattern smears into diffuse rings instead. No sharp structure, no repeating signature, just a haze that looks almost identical to what you'd get firing X-rays through a liquid. That single experiment, repeated for over a century now, is the real proof behind the claim. Not a guess, not a figure of speech. An actual measurable signature that glass's internal structure genuinely does resemble a liquid's chaos, frozen in place. In plain terms, this is what that actually means. When most liquids cool down and solidify, their molecules have time to organize themselves into that repeating crystal lattice. Water freezing into ice is the classic example. As the temperature drops, water molecules slot into a precise, six-sided crystalline structure. That's why snowflakes have that recognizable geometric symmetry. Glass doesn't cool that way. When molten glass, mostly silica, is cooled down, it's cooled quickly enough, and its chemistry is complex enough, that the molecules never get the chance to arrange into that neat, repeating lattice. Instead, the disordered arrangement they had as a liquid gets essentially locked in place as the material hardens. The chaos freezes rather than resolving into order. That transition even has a name. It's called the glass transition, and it's not the same as freezing. Freezing is a sharp, defined phase change. A liquid becomes a crystalline solid at one exact temperature. The glass transition is a gradual process. As molten glass cools, it gets thicker and thicker, more and more resistant to flow, over a range of temperatures, until eventually it's rigid enough to behave exactly like a solid for any practical purpose. There's no single moment where it flips from liquid to solid. It just gets slower and slower until functionally it stops. Glass, then, is best described as a liquid that got frozen mid-thought. Structurally disordered like a liquid. Rigid and shape-holding like a solid. A state of matter that technically sits in its own category. One odd exception is worth knowing, because it proves the whole point rather than breaking it. If you cool molten glass slowly enough that the molecules actually do get time to organize, it can start crystallizing after all. Glassmakers call this devitrification, and it's usually treated as a defect, not a feature. The material turns cloudy, brittle, and structurally weak, losing the clarity and strength that made glass useful in the first place. Manufacturers go to considerable lengths to avoid it, cooling glass quickly and precisely for that exact reason. Which tells you something important. The disordered structure isn't a flaw glassmakers are stuck with. It's the entire point. Glass is useful specifically because its molecules never get the chance to organize. Now here's the part that should genuinely complicate things again, because this is where the story gets more nuanced than a simple yes or no answer. Just because glass isn't flowing in any way that matters to you or your windows doesn't mean it never flows at all. And this is the detail that keeps the myth alive in certain corners of science communication. Because it's technically, mathematically true, just wildly misleading at human timescales. With every material has a property called viscosity, which is a measure of resistance to flow. With water has extremely low viscosity, it flows almost instantly. With honey has much higher viscosity, it flows slowly. With silica glass at room temperature has a viscosity so extreme that the number is almost hard to process. With estimates place it at somewhere around 10 to the 40th power times more viscous than water. That's a 1 followed by 40 zeros. At that level of viscosity, calculation suggests that a pane of glass could, in theory, flow perceptibly, but the timescale required is measured not in centuries, not in millennia, but in timeframes that stretch beyond the current age of the universe itself. Some estimates suggest it would take longer than the roughly 13.8 billion years the universe has existed for room temperature glass to visibly deform under its own weight. A famous real-world experiment captures exactly this idea, just with a different material. At the University of Queensland, a physicist named Thomas Parnell set up something called the pitch drop experiment back in 1927. Pitch is a petroleum-based substance that looks and feels completely solid. You can shatter a piece of it with a hammer. But it's also, technically, an extremely viscous fluid, and Parnell wanted to prove it. He poured heated pitch into a sealed funnel, let it settle for years, then cut the seal and let gravity take over. A single drop fell roughly every 8 to 9 years. Nobody has ever witnessed a drop actually fall in real time, not once, in almost a century of the experiment running. Cameras eventually had to be set up around the clock just to catch it happening, because by the time a scientist noticed a drop was close, it had usually already fallen. Glass isn't quite as extreme as pitch. But the underlying principle, a solid-looking material that is technically still flowing, on a timescale no human patience could ever capture, is the exact same idea. In the strictest, most literal sense, glass is not perfectly permanently solid. It is an extraordinarily slow-moving fluid, if you're willing to stretch the definition of moving to include timescales longer than the universe. But calling that glass is a liquid is like calling a mountain temporary, because erosion will eventually flatten it. Defensible on paper. Practically meaningless. And definitely not something that's going to warp your windows in your lifetime, or your grandchildren's lifetime, or the lifetime of civilization as we currently understand it. That's also why the field of materials science doesn't really argue about whether glass is a solid or a liquid anymore. The old framing is considered outdated. Researchers studying amorphous solids treat glass as its own distinct category of matter, sometimes informally called the fourth state, alongside solid, liquid, and gas. Not a liquid pretending to be solid. Not a solid with liquid tendencies. A genuinely different category that doesn't fit neatly into the two boxes most of us learned in school. Once you understand that glass is defined by this frozen disorder, rather than by whether it's a liquid or a solid, you start noticing that glass is not alone. This same amorphous structure shows up throughout the natural and material world, and once you know what to look for, it's everywhere. Obsidian, the black volcanic rock, is a natural glass. It forms when lava cools so rapidly that its molecules never get the chance to crystallize, and it ends up with the exact same disordered atomic structure as a window pane. Ancient civilizations shaped obsidian into some of the sharpest cutting tools ever made, edges that can, in some cases, outperform surgical steel at a molecular level, precisely because that amorphous structure fractures in an incredibly clean, predictable way. Certain plastics behave the same way. Amber, the fossilized tree resin famous for preserving prehistoric insects, is technically an amorphous solid too. Even some metals can be manufactured into what's called metallic glass. Alloys cooled so quickly that their atoms are locked into a disordered structure instead of the ordered crystal lattice you'd find in a normal chunk of steel or aluminum. Metallic glasses are of huge interest in engineering right now because that disordered structure gives them unusual strength and elasticity properties compared to their crystalline counterparts. Even the glass on your phone screen fits into this story, just a heavily engineered version of it. Manufacturers chemically strengthen that glass by swapping smaller ions near its surface for larger ones, cramming the outer layer under compression. The atomic structure underneath is still that same amorphous, disordered arrangement. The compression is just added on top, like a coiled spring, to make cracks harder to start. That's why a modern phone screen can survive drops that would have shattered glass from decades earlier. Not because the fundamental material changed, but because engineers learned to manipulate the disorder rather than eliminate it. There's also aerogel, sometimes nicknamed frozen smoke, an almost impossibly light amorphous solid made mostly of air trapped inside a silica structure. It looks like it shouldn't be able to hold its own shape, and yet it does, rigid enough to sit in your hand, despite being over 90% empty space. NASA has used it to capture comet dust particles traveling at extreme speeds because its structure absorbs the impact instead of shattering. Different material, wildly different application, same underlying category as a window pane. None of this is just a quirky fact about windows. It's a window, so to speak, into an entire hidden category of materials that don't behave the way most of us assume solids and liquids are supposed to behave. Which brings us back to where this started. Those old windows, thicker at the bottom, are not secretly, slowly dripping downward under your nose. They're artifacts of a manufacturing process from centuries ago, and a practical choice made by the person who installed them. The glass itself, structurally, chemically, is exactly the same today as it was the day it was made. Frozen. Locked. Disordered at the atomic level, but going nowhere in any way that matters to you. This myth survives because it sounds almost true. It borrows a real scientific fact, the molecular disorder of glass, and stretches it into a story that's more dramatic and more visual than the boring, accurate answer. Glass isn't secretly alive, slowly reshaping itself while you sleep. It's something arguably stranger. It's a material caught permanently between two states, neither fully solid nor fully liquid, held in that in-between structure indefinitely, on any timescale that could ever matter to a human being. Notice what made the myth so easy to believe in the first place. It had a visible piece of evidence you could point to with your own hands. An old window in an old building. It had a satisfying cause and effect, gravity, time, motion. And it had just enough real science attached, that molecular disorder, to survive a follow-up question. Most myths that spread don't survive scrutiny for long. This one did for well over a century, precisely because debunking it required understanding several layers of actual physics, manufacturing history, and viscosity, instead of one simple fact you could check in a sentence. So next time someone tells you that old windows prove glass is a liquid, you'll know the real answer. It's not flowing. It's not melting. It's frozen chaos, and it has been since the day it left the furnace. And maybe that's the part worth sitting with. Not that the myth was wrong, myths usually are, but that the truth underneath it is so much stranger than the story people made up to explain it. Nobody needed to invent a slow-moving liquid dripping through your windows for centuries. The real material sitting in that frame is already something science still doesn't fully have a name for. Not quite solid. Not quite liquid. Just permanently, deliberately caught in between.